Induction machines are the workhorses of industry. They convert electrical energy into mechanical energy and are widely used because they are rugged, reliable, and require minimal maintenance. They are called induction machines because the rotor currents are induced by the rotating magnetic field, not supplied directly. 1.2 types. Three-phase induction motors. Single-phase induction motors. Three-phase induction motors are more common in industrial applications, while single-phase versions are used in domestic appliances. 1.3 Principle of operation. When a three-phase supply is applied to the stator windings, it produces a rotating magnetic field, RMF. This RMF sweeps past the rotor conductors, inducing an electromotive force due to relative motion. The induced currents produce their own magnetic field, which interacts with the stator field to produce torque. 1.4 Rotating magnetic field. The RMF rotates at a speed called the synchronous speed, given in verbal form as synchronous speed equals 120 times supply frequency divided by number of poles. The rotor always rotates at a slightly lower speed than synchronous speed. The difference is called slip, and it is essential for torque production. 1.5 EMF equation of an AC machine. The induced EMF per phase in the stator depends on the number of turns, the flux per pole, the frequency of supply. This equation parallels the transformer EMF equation because an induction motor essentially behaves like a transformer with a rotating secondary. 1.6 Torque production. The torque developed in an induction motor depends on rotor resistance, slip, and air gap flux. The torque speed curve is a key performance indicator, showing high starting torque for certain designs and constant speed over a wide load range for others. 1.7 Equivalent circuit model. The induction motor can be analyzed with an equivalent circuit similar to that of a transformer, with additional elements to account for rotor slip. 1.8 Torque speed characteristics. The curve has three main regions. Starting, high slip, lower speed. Pull-out torque, maximum torque the motor can develop. Running, normal operating region with small slip. 1.9 Starting methods. To limit inrush current and control torque, different starting methods are used. Direct online starting, small motors. Star-delta starting. Auto-transformer starting. Rotor resistance starting, wound rotor motors. 1.10 Speed control. Induction motor speed can be controlled by changing supply frequency, most efficient, used in VFD drives. Changing the number of poles. Rotor resistance variation, wound rotor types. Voltage control, single-phase types. 1.11 Single-phase induction motors. Single-phase induction motors are not self-starting because the single-phase RMF splits into two opposing fields. To achieve starting torque, auxiliary windings and starting mechanisms are used. Split-phase motors. Capacitor start motors. Shaded pole motors. Applications include fans, pumps, washing machines, and compressors. 2. Synchronous machines. 2.1 Introduction. Synchronous machines operate at a constant speed, the synchronous speed, regardless of load, as long as they remain in synchronism with the supply. They can function as generators, most large-scale electricity generation, or as motors. 2.2 Construction. Main parts include stator, stationary armature winding carrying the AC output or input. Rotor, field winding excited by DC, producing the main magnetic field. Slip rings, for supplying DC excitation to the rotor winding. Frame and cooling system, for mechanical support and heat dissipation. 2.3 Types of rotors. Salient pole, for low-speed, high-pole applications, hydroelectric generators. Cylindrical rotor, for high-speed applications, steam turbines. 2.4 Operating principle. When the rotor magnetic field locks with the rotating magnetic field of the stator, the rotor turns at synchronous speed. In generator operation, mechanical input, turbine, drives the rotor. In motor operation, AC supply and DC excitation maintain synchronism. 2.5 Armature windings. The stator armature has distributed windings arranged to produce a balanced three-phase output or input. 2.6 Equivalent circuit. Similar to transformers but with additional terms for excitation voltage. The phasor diagram is used to study performance under different load conditions and power factors. 2.7 Voltage regulation. Voltage regulation measures the change in terminal voltage between no load and full load at constant speed and excitation. 2.8 Parallel operation of generators. For reliability and flexibility, multiple synchronous generators are operated in parallel. Conditions for synchronization include equal voltage magnitude, equal frequency, same phase sequence. 2.9 Synchronization. Performed using synchroscopes or lamp methods to ensure proper phase alignment before connecting to the busbar. 2.10 Power angle characteristics. The power developed depends on the load angle, the angle between rotor and stator magnetic fields. Overloading beyond the stability limit causes loss of synchronism. 2.11 Effect of field excitation. Changing DC excitation alters the power factor. Synchronous machines can be used for power factor correction by operating over or under-excited. 2.12 Synchronous motors. Operate at synchronous speed. Require starting methods, since they are not self-starting. Applications include constant speed drives and reactive power compensation. 2.13 Hunting and damper windings. Hunting is the oscillation of the rotor about synchronous speed due to sudden load changes. Damper windings reduce these oscillations. 3. Special purpose motors. 3.1 Stepper motors. Operate in discrete angular steps. Controlled by input pulses. Used in CNC machines, robotics, and printers. 3.2 Universal motors. Operate on both AC and DC supply. High speed and compact. Used in portable power tools and appliances. 3.3 Shaded pole motors. Simple single-phase motors. Low starting torque. Used in fans, blowers, and small appliances. We've covered induction machines, synchronous machines, and special-purpose motors, focusing on principles, construction, performance, and applications. Together with Module 1, you now have a complete overview of electrical machines, from transformers to motors, enabling you to understand, operate, and analyze the key machines that drive our modern world.